Okay, so we'll get started here. One thing I wanted to mention before we get too far into things, if you go to the YouTube page, and I think this is one of my other sections, but I did the same thing for you guys. I put kind of a description, select a different video, kind of on each video, at least kind of since the last exam, about what it covers. Specifically also identifying if we did some work in Excel. Also, if you go to the lecture files, when I upload these, I'll start putting kind of the names of what the slides cover as well, just kind of talking with a couple of students. I always try to listen to feedback and kind of thinking about going into this next exam, probably a little bit easier to kind of identify where things are if you're working on homeworks, figure out exactly what slides or what video might be the most relevant, okay? I'll also be posting after, well, not this class, but my classes today, the next Excel assignment. So that'll be the last thing that you have. We have a Connect assignment right now that you could already do the first few problems. It's just confidence interval stuff. You could start working through the hypothesis testing questions. I'll also give you an Excel file that'll be, or Excel assignment that will be due prior to the exam as well. Okay, so you got about 2 weeks to kind of do both of those leading up into that exam. I would kind of suggest trying to do them next week, kind of get them out of the way. We'll really have covered, everything that you really need to do them after either today or Monday. And so I would suggest trying to get those done that week, next week, and then you'll have kind of that next week to start preparing for the exam. Okay, so we left off kind of talking about sample proportions and doing hypothesis testing with them. So we worked through one example with kind of this guns. We'll kind of start with this example, work through it, then we'll go to Excel, look at some hypothesis testing questions in Excel for proportions, but also for sample means when we know the variance. So we're going to be doing both types today. So let's say you want to test against the hypothesis that less than 15% of Indiana mothers smoke while pregnant. You take a sample of 400 mothers, you find 72 smoke. Now, if I didn't give you this sample proportion, like let's say I left that off, and I then asked you what the null and alternative hypothesis are, well, first of all, just to identify the null and alternative, you shouldn't need that sample proportion, right? So you shouldn't need that. All you need is this value that you want to test against. Now, one thing that I won't write the exam this way, but when we think about what we want to test against, I mentioned this probably a couple class periods ago, what I want to test for is the alternative hypothesis. What I want to test against, that's my null, okay? So here I have phrased it slightly different than I have it in the other examples. Up to this point, I've always told you what you're trying to test for, which if I'm wanting to find something or I'm wanting to test for something, I assume the opposite is true. And what I assume, that null hypothesis, what I assume is true, that's what we say we're testing against, okay? So here, when we want to test against the hypothesis that less than 15%, that's identifying our null hypothesis. So there we want less than, and then we always include that equality sign on the null hypothesis, so less than or equal to 0.15, okay? Which means the alternative hypothesis would be, is that true population proportion greater than 0.15, okay? We then take a sample. If I didn't give you the sample proportion, well, if you know that 72 out of the 400 mothers that were sampled smoked, to get your sample proportion, you simply take 72 divided by 400. Right? So that's how I got that 0.18. So if this is our null alternative hypothesis here, what type of tailed test do we have? We have a greater than sign in the alternative hypothesis. We have a greater than test or a right-tailed test. Right? So I'll usually kind of refer to these as left and right-tailed, because remember, when we're thinking about how do we find the critical values and how do we find p-values, well, it kind of differs a little bit whether or not we have a left or right-tailed test. And really, for that left-tailed test, if we remember what we were doing with critical values, if I have alpha values, right, that we typically see of 0.1, 0.05, or 0.01, right, that's always going to have a very small area in that lower left tail, right, if this is alpha. What I was wanting to find was the critical value that gave me alpha in that tail. Well, remember, the standard normal distribution has a mean of 0. So what's going to be true about all the critical values for a left-tailed test? They're all going to be, they're below 0, negative, right? Same idea if we had a right-tailed test, all my critical values would be positive, right? We don't have a right-tailed test here, so. Okay, so I have a right-tailed test, sorry, I have a left-tailed test, so I know I'm going to have these negative critical values, right? And that's why I start calling it left-tailed tests, right? Because this was for an alternative hypothesis that had a less than sign, so a less than test, but we're dealing with the left tail. That's why saying a left-tailed test kind of helps us remember that, right? All right, so if we look at the information we're given, right, the first thing we wanted to do is identify the null alternative. So we did, we know what type of test. Next thing is what's my alpha values? Well, I'm giving you 3 alpha values here, so we can actually do the hypothesis test for the 1, 5, and 10% significance levels, all right? So how would I find those? Well, it's what would give me alpha in that lower tail. Well, we already said we know they're negative, so here I could actually rule every single answer out except for B. Right? Now, how do I actually find these 3 values? Well, let's start with that 1% level, so an alpha of 0.01. We could go to the standard normal table. We know the area that we want in that lower left tail is 0.01. It's in between these 2 values. So negative 2.32 and negative 2.33. We're going to the second decimal. I said just always use kind of the higher of those 2, or the higher in absolute value. So 2.33. That's how we found that first one. We do that exact same process, but now we look up 0.05. We'd find the corresponding z values. Sorry, this is, my thing's around here. Should be down here, right? I found negative 2.33. I look up the next 0.05, corresponding z-value is negative 1.65. I look up 0.1, corresponding z-value is negative 1.29, right? But I would use that same process. But really, once I looked up one of these, I didn't, to identify the correct answer out of these 4, I wouldn't have had to do any more work, even if there had been some negative signs on the other values. Right? So that's how I look up my critical values, right? Now, what's going to be true, and I think we have a summary slide way back here. Here we go. They're always going to be the same 3 values, right? If we're looking at the same 3 alpha values, we're always going to find the same 3 corresponding z-scores, right? Negative for a left-tailed test, positive for a right-tailed test. Now, for a 2-tailed test, that was where we had to divide alpha by 2, because alpha is the total area in the tails, right? If I have multiple tails, it's a total area in the tails, so I had alpha over 2 in each tail. Okay? We'll go through some examples of 2-tailed tests in Excel as well. So we're down here. We've got our critical values. Oh. Oh wait, did I mess that up? Hold on, let me see. Oh yeah, sorry. Why was I doing a oh, because the example I was doing on the board was a left-tailed test. Sorry. You're right. It is a right-tailed test. So this is our right-tailed test. So this was correct. I was going to say it's kind of weird that I didn't have that. Sorry about that. I'll tell you why I made a mistake there, because I got tripped up. I was drawing this out for you just to give you an example of a left-tailed test. The actual problem we had was for a right-tailed test. So everything I was saying is the exact same thing, except we would want alpha in that right tail, right? So if instead I was looking up critical values for a right-tailed test, what's the problem? If I looked up 0.01, well, the table always is looking at the area to the left. So if I want, say, 0.01 in that upper right tail, how do I find that critical value? Well, I would actually have to look up 0.99, right? So if I go ahead and do that, this is will actually be good. It'll kind of prove to you something. So I go down here, I look up 0.99, closest I can get is right here. So 2.32 and 2.33. So I found 2.33 here because the example was a right-tailed test. Sorry about that. When I went to the board, I mixed that up, right? So we have this right-tailed test, but notice, if I didn't want to worry about oh, I got a right-tailed test, I'll subtract alpha from 1, look that value up. Whereas if you draw it out, I think that's pretty clear in the visual. Well, remember, it's a symmetric distribution. So if I had simply looked up alpha, and then just remember, I would have found negative 2.33, and then I would just remember, oh yeah, I'm dealing with a right-tailed test, so it'll be that value, but positive, right? So either way, whichever way is easier for you to do, I think if you're drawing this out, you kind of remember, oh yeah, the table tells me the area to the left, so if I want this value directly from the table, I'd have to look up 0.99, okay? Sorry about that, thanks for saying something. I mixed those up. So we've got our 3 critical values. So what we're going to do now is plot those, okay? So let me just redraw this. It's getting a little messy. We've got our 3 critical values. They were 1.29, 1.65, and 2.33. Remember, these corresponded to alphas of 0.1, 0.05, and 0.01. We think about our rejection regions, right? It's going to be anything to the right of those, right? So we can test against 3 different alpha values or 3 different significance levels kind of all at the same time. Now, last class, if you remember, how did I know that this was my rejection region? Well, I'm always going to look at, for a right-tailed test, it's going to be the area to the right of my critical values. Left-tailed test, area to the left. Two-tailed test, areas to either side of my critical values. Really, a non-technical way to remember this is, once I plot my critical values, draw arrows into the tail. Right? That's probably the easiest way to think about it. Okay? So now I've got my critical values in my rejection region. I need to come up with what my test statistic is. So I go back, I look at the information. Right? I know that I should be for proportions using this equation, right? Remember, the standard deviation, the denominator here represents the standard deviation of my sample proportions. Okay? So I can calculate that first and then plug it into the denominator, or I can just do it all at one time, right? So I go back to my problem. I found a sample proportion of 0.18. The assumed true value from our null and alternative hypothesis was 0.15. I plug in 0.15 and 1 minus 0.15 here, divide by my sample size, and I get this positive test statistic, right? And that makes sense. I found sample evidence that was above the assumed true population proportion, right? Now, that population proportion is the mean of the distribution for my sample proportions. So I found something above the mean of my distribution, so I should be a certain number. Remember, our Z statistic, our test statistic, is still coming from a standard normal distribution. So the interpretation is still the number of standard deviations above the mean of the distribution that the sample evidence that I found was, right? So here it's 1.68 standard deviations above that assumed true population proportion, which we know is the mean of our distribution, right? Just as kind of a reminder, I was drawing the standard normal distribution here, but really the original, well, I can draw underneath here. The original data, right, was not sample means, was sample proportions. I saw 0.18. The assumed true value was 0.15. So I need to turn this into a Z-score. I didn't quite get this to scale because the Z-score that we just found was 1.68. So I just plot that, right? Once I have that test statistics, it's a Z-score, so I plot it against my critical values. I can see here, it's in the rejection region at the 5% significance level. It's in the rejection region at the 10% significance level, but it's not in the rejection region for that 1% significance level. So we would say we can reject the null, and if we have 10, 5, and 1% significance levels, we said that's 90, 95, 99% confidence levels. So with 90 and 95% confidence, I could reject that assumed true value, but I couldn't reject it with 99% confidence, okay? Any questions on that? We're okay with that? Now, what could I have also done? I could have also took my test statistic of 1.68 and found the p-value, right? That red area kind of representing my p-value. Hopefully, I get the same rejection decisions if I do that. So let's look up 1.68 on our table. So 1.6, go over to 8, 0.9535, right? So 0.9535, the table always tells me the area to the left. I wanted the area to the right, so I subtract it from 1, right? So I wanted the area to the right here, 1 minus 0.9535 or 0.0465 is my p-value. Maybe rid of this so I can write something out for you here. So we only reject if the p-value is less than alpha. So is 0.0435. That's less than 0.1. Yes, so I can reject at the 90% level, confidence level. Is it less than 0.05? Yes, so I can reject at the 95% level. Is it less than 0.01? No, it's not. So I would fail to reject at the 99% level, which is the exact same thing that we said with the critical values, right? And I kind of went through a little thing last class just to show you why we always make the same decisions, because we're really just comparing either the test statistic to the critical values, or we're comparing, remember, this critical value, the area to the right of it represented alpha, and the area to the right of my test statistic represented the p-value. So it's kind of like just comparing things on 2 different dimensions, right? And that's why we always end up making the exact same decision. Okay? Any questions on that? We're okay with that? We're sure? Okay. Let's do, and I'll use the board as we go through these Excel examples to kind of show you, if you did it by hand, what it would look like as well. So let's go here. I think, wait, let me double check. I think that was the, yeah, and then I kind of have the rejection decision here, and then we've got some of the next topics. So I want to go to Excel. I believe you should see 2 files up there. I might have only posted the one just so you didn't get, so let's go to in-class data. So look at this hypothesis testing one. Right? I have one that's blank. If you want to kind of work along with that blank one, I'll just upload that right now. I just didn't want to kind of confuse anyone why there was there was nothing in there. So let's go, here we go. So if you want to kind of work along with me, you can use this hypothesis testing blank file. After we've gotten through everything, not just today, but also some work that we'll do next week, the hypothesis testing will have kind of everything filled in. Hypothesis testing file, okay? So let's go to, since we're doing proportions, let's just start out with a proportion example, right? So we can kind of keep some continuity here. I'll zoom in a little bit so we can see everything. All right. Now I said it's blank, you should still have some values in there. For right now, assume, I know I've got a data set and I've given you some data that's much larger than a sample size of 100, but I want to show you if you only had a sample size that was smaller, what it would look like, and then we'll use the actual kind of sample size. So here, we're using this sample size of 100 just to kind of prove a point at first. Well, if we want this sample, I have this data on, it was high school students in their senior year, and questioning of whether or not they ever tried e-cigarettes. I don't think, actually, it might not have been just high school students. I think it might have been all middle high school students. And so if we have this 1, 0 variable, 1 if they've ever tried it, 0 if not, we could actually just find the sample proportion by taking the mean, or in Excel using that average function. Okay. Then let's say I want to do a right-tailed test. So I can think about this as my null hypothesis and my alternative hypothesis. So my alternative hypothesis is that the population proportion, right, is less than or equal to 0.25, right? No, I was in the wrong cell. Sorry, that was my alternative hypothesis. So let's assume the alternative hypothesis is that it's greater than 0.25, which would mean my null is that the population proportion is less than or equal to 0.25. Okay. So we have a right-tailed test here, right? Greater than sign of my alternative hypothesis, and I'm testing for whether or not the proportion of students who have ever used e-cigarettes is greater than 25%, essentially, right? Or a proportion of 0.25. So the first part of doing this in Excel is really just using Excel as a calculator. When you're calculating your test statistic, we're just entering in that formula and selecting on the things that we would want to plug the numbers into that formula for. Selecting the cells that exist in our Excel worksheet. So how do we find the test statistic when we're dealing with a sample proportion? So we take the sample proportion we found, we subtract the assumed true sample proportion, which I had it entered into a cell up here, and I'll show you why once we get to the end of the example, why I didn't just type 0.25 in here, okay? I then divided that by the square root of that assumed true population proportion times 1 minus that assumed true population proportion divided by my sample size here, okay? So that was me just using Excel to put that formula in, right? So on this Excel assignment I post, they're Excel assignments. I don't want you to do this by hand. I want you to enter this in and use Excel to do the work, okay? So we've got this test statistic equation, all right? We've got it entered in. So we now get our test statistic. So let's visually think about what we're doing here. We have a right-tailed test. We've got the distribution of our sample proportions. Should be centered around 2.5, wasn't it? Whatever we assumed the true population proportion was. We found a sample proportion, I think it was 0.33 something. Right? We have a right-tailed test, so we want to know what's the probability that we saw the sample proportion of 0.33 if the assumed true value of 0.25 was in fact the true population proportion. That probability of seeing something that far away from the assumed true proportion, or something even further, that area represents our p-value, right? That's literally the definition of the p-value. The probability that we saw sample evidence that was as far away from the assumed true value as we did, or something even further away from that value. Right? What we're then going to want to do, if we're using the p-value approach, is turn this in to a z-statistic or a test statistic and find the area to the right, because that would represent the p-value that we wanted to originally find, right? We started out with a normal distribution. Well, we can't do much of that. We have to convert it. So we'll then go to a standard normal, and then we can find that p-value, okay? So how do we do that in Excel? Well, we've kind of already done this before. If I have a z-value and I want to find the probability or the area to the right of it, well, I know that to find the area to the left, I can use this norm.s.dist, because remember, this test statistic, we also were calling it a z-statistic. It comes from that standard normal distribution. So here's the z-value that I want to find, and it will return to me, comma 1, the area to the left of it. I wanted the area to the right, so 1 minus that, right? That norm.s.dist will tell me the area to the left of my test statistic. I want the area to the right for this right-tailed test, and so I have to subtract that from 1. Okay? Any questions on that? So that should return to me my p-value, right? Now, with the p-value, I could already start to make my rejection decision. Right? Now, I'll show you how to use an if statement in Excel, and it kind of is nice for making rejection decisions, especially if we wanted to set this up so that we were like testing against several different alpha values. In fact, I didn't do that in the file, but I'll set this up for several different values and show you why this is kind of helpful. So 0.1, 0.05, and 0.01. Okay. So these are actually, just to be clear, let's move these over and type alpha in here. And then we'll move our rejection decision down one line. Okay. So what I'm going to do is, okay, use this if statement and test for, well, what's our rejection decision? If our p-value is less than, oh, and it's doing this thing again. I don't know why it does this on my laptop, but not in my office. So what that is, cell G9, right? So it's, for some reason, it's kind of overlapping here. But I want to test for whether or not that p-value is less than the alpha value. Right? If it is, so the very first thing you say is, okay, if that's true, what do I want to show up in this cell? Well, I want the word reject to show up. If I want a word to show up and not a number, I have to put it in quotation marks. Okay? If it's false, if the p-value is not less than alpha, well, then I'd be failing to reject. So I'm just going to put fail to reject here. Okay? So what this does is it checks whatever the first statement you put in there. If it's true, it'll return the first thing, kind of comma, whatever first word you put in there. If it's not true, it'll put in the second one. So this should give us our rejection decision. Okay? Now this is kind of makes sense, right? Our p-value of 0.02 is definitely less than an alpha of 0.1, so we should be rejecting there, right? Now, if I copy this over, what's the problem going to be? Well, it looks like everything's working okay, but it's actually just using this value or this cell, which there's nothing in it, so it treats it as 0. So what do we have to make sure that we do if I'm copying it over here? Well, I want my alpha to update, so I want that cell reference to update, but I don't want my p-value to update, so I'll put $signs around that. Okay? Hit enter. Now when I copy this over, sure enough, it keeps that p-value cell reference the same. Okay? I'll then drag it over one more. Now notice, is our p-value of 0.02 less than an alpha of 0.05? It is, so we would reject at the 5% significance level, or 95% confidence. But our p-value of 0.02 is not less than 0.01, so we would fail to reject, right? So that's kind of a nice way to set it up using like that if statement in Excel. You know, we've used the count ifs before. I don't think this one's that much tougher. One of the kind of key things is that if we want to put text, we have to put quotation marks around it, okay? Now, I could also do the critical value approach. Now, the problem here is if I'm doing it in one cell, I'm only going to be able to test it against one level. So let's say I test it against the 90% level. Well, to find my critical value for the 90% level, what we're really saying is, okay, I know the area in the tail that I want. The area in the tail, if I'm trying to find my critical value, so I'm dealing with that standard normal distribution, I want the critical value that gives me whatever alpha level I set. So our alpha here was 0.1. So by hand, what we would do is look up on the table the area to the left, which was 0.9, and then it would return to me my critical value. Well, we can do the same thing in Excel. It's just instead of using that physical table, we need to use the function in Excel that does that for us, which is norm.s.inv. Remember, this was the function that if I told it the probability I wanted in that lower left tail, it would return to me the z value that would give that to me. Right? Well, here I wanted 0.1 in the upper right tail, which meant 0.9 in the lower left tail, so 0.9. Right? And now I've got my critical value. Okay? So that's how we could find critical values in Excel. That's how we could find p-values, make our rejection decisions. Now, for a right-tailed test, what I could have also done here, just to show you, is say, okay, look, if that test statistic is greater than my critical value. Now, I'll put my critical values here. Well, let me do this first. Let's do, and set this up kind of nice. So let's do norm.s.inv, and then select 1 minus alpha, because we have a right-tailed test, right? So for this first one, it would be 1 minus 0.1, right? That's exactly what we did in this cell, so it should give me the exact same value, right? But now, when I copy this across, the cell reference updates to be the new alpha. So here's a row of my critical values. So for my rejection decision, I could have also done if my test statistic is greater than my critical value, right? Then it would be in the rejection region for a right-tailed test. If it is, then put reject. If it's not, fail to reject, right? So this, hopefully, now when I copy this across, well, I want my critical value to update, but not my test statistic. So I'll freeze that cell reference for the test statistic. Now if I copy this across, hopefully I get the exact same rejection decisions as when I set that if statement up for the p-value. Right? So all I'm really doing there is using that if statement to do what I was doing before with kind of that visual of plotting my test statistic, plotting my critical values and the rejection regions. If the test statistic's in the rejection region, then we reject. Right? So for the first one, we get the exact same rejection decisions, right? Because we're just comparing, instead of kind of comparing our p-value to alpha, we're comparing our critical value to whatever, z statistic that we ended up finding, right? Okay. Any questions on that? Here, I'll go back to Excel too. You want to see one of these cells again, or yeah? So not confidence interval. We want to be careful.
Okay, but like the rejection decision. So like, is that saying we rejected it to 90% and 95%?
Yep.
But why would we fail to reject it at 99%?
Because if I can reject something with 90 and 95% confidence, I might not be able to reject it with 99% confidence. Like if I told you right now, anything, like I told you, I don't know, with 90% confidence, I can tell you that the sky is green. Well, you might be able to say that with 90% confidence, but can you say it with 99% confidence, right? Because that's an even higher level. So I might be able to reject the null at 90%, right? Saying the sky is green. I'm rejecting the null that the sky is blue, but I can't do that at the 99% level. Yeah. Now, if it's working in the opposite, if I can say something with 99% confidence, then I can say it with any level of confidence below that. Yeah. No, I got, yeah. Any other questions? We're going to see a cell again. Okay. So we did a little bit more work there than even in the complete file that I uploaded. The complete file is just like a little bit more clean if we had one specific alpha value. Yeah. Oh, yeah. Yep. Yeah, and those are probably the ones where you've got the formula in front of you. It's just a matter of making sure you're kind of entering that formula into Excel, okay? It'd be nice if there was a built-in formula to calculate that test statistic for a sample portion example, but they don't have one. So.
Is that up on Canvas?
So, right, if we go back, well, I mean, in one of the examples that we did here, right, that was that formula. Yep. Any other questions? So this is kind of interesting. We can say, with 90 and 95% certainty, based off our sample, more than a fourth of kids have tried these things, right? Or, which is maybe not a good thing. So this is, I thought it was a somewhat interesting data set, so I figured we'd take a look at that. All right, let's do another example. So I think maybe we've used this before, but this BMI data. Oh, sorry, before we move on, I forgot that I used this sample size of 100. So why did I do this? Because when we have relatively low samples, notice that even when I find a sample proportion that's quite a bit higher than that, hypothesized true value, I can't reject that as being the true value with 99% confidence, even when I have a really high, pretty high sample size. But notice the actual data, the actual sample size, if I use that count function, and then I select my variable, the actual sample size was huge. I had like 18,000 here. So if I can get a really large sample, well, now notice, even using that same sample evidence, because it was from a much larger sample size, which I know will greatly reduce the variance of my distribution of my sample proportions, right? Then I can actually be able to, with the same sample proportion, be able to reject that same hypothesized true value with 99% confidence, where I couldn't before. Does that make sense, or is there any questions on when I'm getting it there? So I put in the fake sample size so that we can have like an interesting result. Obviously, when I take a sample of like 18,000, now notice I use the cell reference because I could start to say, well, is it greater than not just 0.25, is it greater than 0.3? Well, I can still reject it at 99% level, right? Well, what about 0.32? I can still reject everything, right? I can actually say up until I get to like 0.33, which my sample portion was just barely above that. But, I can really narrow down like what values I can reject when I have a really high sample size, right? With that same sample evidence, remember before when my sample size was 100, I couldn't even with 99% confidence reject 0.25. But now, with that higher sample size, I can. And in fact, I can with 99% confidence reject that it's less than or equal to 0.32, right? So having this higher sample size really allows us to kind of have more power in what values we can reject, okay? So let's move on to an example where we have a population variance and somehow we know when we're looking at where the population mean is and somehow we know the population variance, right? Somehow it's given to us, right? So I have this sample. I'm going to calculate my sample mean for BMI here, right? So I'm just going to select that. I'm also going to make sure that you guys can see things, right? So based off this sample mean, right, let's do a left-tailed test. So what I'm going to set up here is the population mean greater than, greater than or equal to 30? That'll be my null. My alternative hypothesis will be, is that population mean less than 30, right? So what I want to test for is whether or not the BMI in the US is less than 30. So I assume the opposite is true. I assume that it's greater than or equal to, okay? And I think this 30 is the cutoff for being considered obese. So I believe that's why I chose that cutoff value. So here, our test statistic equation is going to be a little bit different. So if we go back to last class, and we're dealing with these sample mean examples, here was our test statistic equation. Take the sample mean, subtract the assumed true mean, just like we took the sample proportion, subtracted the assumed true proportion. And then we'll be dividing by, now we're not dividing by the standard deviation of our sample proportions, we're dividing by the standard deviation of our sample means. The equation we had for that was the square root of our population variance over our sample size. So that's what we're going to enter in here. So we're going to take, I have to put in parentheses, our sample mean that we found, subtract our hypothesized true value, or our assumed true value for the population mean, divide that by the square root of the population variance we were given, divided by our sample size, okay? So we're going back to kind of the other type of examples that we looked at last class. So this should give me my test statistic, right? So I get a negative test statistic because I found evidence that was below the assumed true mean. Well, I'm dealing with a left-tailed test now, right? I've got this hypothesized true value of 30, and I found a sample mean of 29.5. So now, what am I doing? I've got a left-tailed test, I know the distribution of my sample means should be centered around whatever that assumed true population mean is, or it would be if it was true. I found 29.5 as my sample mean. Left-tailed test, I want the probability that I saw something that far below the assumed true mean, or anything even further away. That probability is my p-value, right? So how can I find that p-value? We use that test statistic equation to find what our test statistic or our z statistic is. I can then look that up in the table. This area would then give me the p-value that I wanted. Now, we could do it by hand, but we can also do this in Excel, like we just walked through an example. In fact, for a left-tailed test, it's a little bit easier, right? So if I have my test statistic, enter that equation in there. How can I find the area to the left of that in Excel? I just use the norm.s.dist, right? I've got the z value, right? My z statistic, comma 1 tells me the area to the left. Well, for a left-tailed test, that's all I wanted. I'm done, right? So I get a p-value of about 0.21, right? I could do my rejection decision here. I'm not going to set it up for every single alpha value like I did the other one. But I could say, okay, look, if my p-value is less than, and here I've got the 95% confidence level, so my alpha would be what? 95% confidence would be 5% significance, so an alpha of 0.05, right? So if that's true, put reject. If that's false, put fail to reject, right? Kind of separated by commas there. So I'm only going to do this for one level here, which is the 95% confidence. You could set it up similar to the first one that we did and do several alphas by like setting up column headings and copying it across. But here we're just going to do one level, all right? And I could have also found my critical value for that 95% confidence level. Well, my critical value there, when alpha is 0.05, for a left-tailed test, so we're looking at the standard normal distribution, we want to know what critical value gives me alpha in the tail. Well, if I know the alpha in the tail I want is 0.05, what function can I use in Excel to tell me what z value, or what z value, what critical value would give me the area of 0.05 in the tail? So I could use what function in Excel? We just used it before. So not norm.s.dist, but norm.s.inv. The area one in the tail was alpha, which we said for this example was 0.05. And I get that critical value of negative 1.6, right? So my rejection region for a left-tailed test is anything below that negative 1.6, right? So once I have that critical value, the rejection region is anything below that. If my test statistic is somewhere down here, I would reject. So we could set up the rejection decision for this one. What we're really looking for is if that test statistic is less than, right, because now we're dealing with negative values. If my test statistic is less than my critical value for a left-tailed test, then I reject. So I could use the if statement and say, look, if my test statistic is less than my critical value here, put the word reject. If it's not, put the word fail to reject, right? So hopefully I get the same rejection decision that I did when I was using that if statement, but doing it for the p-value approach, right? Sure enough, we get the same decision, right? Any questions over any of that? We're okay with all this? Now, once again, I gave you a fake sample size here. We have a much larger sample. So let's see what happens, right? Even at the 90% level, I failed to reject, right? Actually, in fact, I would fail to reject even at the 20% level here, right? At the 20% significance level or 80% confidence level, the alpha would be 0.2. My p-value is not even less than 0.2 here. So let's instead actually see what the real sample size was. Oh, wait, actually, oh, maybe I didn't include the real data. I think I actually just deleted it so we had a smaller sample. Okay, I can't show you that with this one then. This was the actual size of the data. So you can see, even with almost 150 people, I really can't, I don't have a lot of strength to be able to reject certain values if my sample size isn't relatively large. Now, the sample mean that I found is relatively close to that hypothesized true mean. So even though I can't say that the population mean isn't greater than or equal to 30, I might be able to say that it's not greater than or equal to, I don't know, 35, right? Oh, okay, I can reject 35 as the assumed true mean. Well, why? Because when I'm thinking about if 35 was the assumed true mean, it'd be way less likely I saw a sample mean of 29.5 than if the hypothesized true value was 30, right? Well, then it would be pretty likely I see 29.5, right? That's pretty close to 30, okay? So, you know, we could test, you know, that's another thing that's nice about using these cell references. I could just jump from doing a hypothesis test for 30 to 35 pretty quick, and I don't have to redo all the work, right? And I can almost kind of narrow down, okay, what's the last value that I can kind of reject as the true population mean for BMI in the US? Well, I can reject 34 at the 95% level. I can reject 33 at the 95% level. I can reject 32. I can reject 31. Okay, I can't reject 30, right? So we were pretty close, but you know, we can really only reject that the true population mean is 31 or greater, but we would fail to reject that it was 30. Any other questions on anything in Excel? You want to see another cell again, or hopefully, you know, you can kind of see it's actually like a lot of things that really the only thing new that I showed you here is this if statement. We've been using the norm.s.dis and the norm.s.inv. It's really just using the table, but doing it in Excel. All right, so everything we've been doing by hand, it should translate to Excel pretty easily, okay? So next week, we will start off looking at when we have an unknown population variance or we have only a sample variance. So we'll go through some examples by hand. We'll do some more Excel work. But for now, I'll get that next Excel assignment up when I'm done teaching today. You can start plugging away on it. It's got some confidence interval stuff. It's got some hypothesis testing stuff. And really, since, like I said, it really translates to what we're doing by hand. Hopefully it'll just be like kind of good, getting more problems and more examples like leading up into this exam. Because I'll tell you right now, like a healthier part of the exam will be hypothesis testing and confidence intervals. And so getting more practice with that, I think will be beneficial, okay? All right, any questions for me? Otherwise, I'll let you guys get out of here. Have a good weekend, and I will see you on Monday.